Hello, everyone. Thank you for joining us. My name is Robin Sweeney, and I'm a strategic account manager for Unchained Labs' particle analysis portfolio. I will be your moderator, and again, I thank everyone for joining us today. Before we get started, I just want to let you know we will have a Q&A session at the end of the presentation. To ask any questions, all you have to do is click on the Q&A in the Zoom navigation bar at the top or bottom of your screen. And then once you do that, you can type your question. You can do that at any point throughout the presentation. And we will get to as many of them as we can. Now, I'd like to introduce Joe Barco, our Senior Director of Marketing at Unchained Labs. Today, Joe will take us through how Hound can help you see, image, and identify subvisible particles. So with that, I'll hand it over to Joe.
Thank you, Robin. Thank you, everyone, for joining us today. So today we're going to talk about plastics. So those of you of a certain age, I had to explain this movie to a couple of my younger colleagues, will remember a movie called The Graduate from the 60s, where in the scene, very iconic scene from the movie, Mr. Robinson is telling Benjamin Braddock, who's a young Dustin Hoffman, to go into plastics because it's going to be a booming industry. And he was absolutely right. So in the last 60 years, there's been an exponential growth in plastics manufacturing and applications. And so much that right now there's about 300 million tons of plastic that's produced annually. Unfortunately, as you know, that plastic doesn't just go away and disappear. And inevitably, about 8 million tons of plastic ends up in the ocean. And that's every year. And so it's kind of a hard number to grasp. There's nothing that we can say that's 8 million, and even finding some comparison, but is hard. But think about it this way. So you have one of these 20-ounce soda bottles, and that's about a little less than half an ounce. That's basically the equivalent of 1 million of these bottles ending up in the ocean a day for the entire year. So huge amount of plastic. And unfortunately, and we've been told from younger ages that we shouldn't pollute, and we have pictures like this that are all over the place. And as we learned a lot, this is actually the best case scenario, but that's not really what happens. Is that a lot of the plastic that ends up in the ocean is actually from all sorts of applications that we have in the house, like from soaps and detergents and washing clothes, and all of that ends up not like this, which is relatively easy to scoop out, but more like this, which are microplastics, which are generally particles defined that are under 5 millimeters in an individual dimension. Most of those, unfortunately, are also not even in a visible range to work with. And over 60 years of plastics consumption and usage, these microplastics have been kind of shown up everywhere. And basically every surface, every body of water is essentially a repository for microplastics. And even in remote areas that are very much not traversed by humans, there's plastics. And so they're going to be with us for a very long time and with unknown consequences to the environment. And as a result, we kind of need to think about how we're going to identify where these plastics are and how what to do about it, right? And so in this scenario, there's a lot of challenges in terms of essentially identifying how to work with and do analysis methods for this, because the problem is only going to get worse. Like, so maybe even if we kind of flatten out our plastics production, over time, we still have a lot of particles. And as that plastic, to some degree breaks down, the challenge becomes harder because particle size will inevitably decrease, but the number of particles will increase. And so that is going to be a challenge for identifying how to mitigate a cleanup strategy, or identifying how the problem, how much the problem is going to present itself. And that has a lot to do with how we collect and analyze those samples. And so this is a study that was done in 2014, where they used essentially retrieved plastics from seawater, and they didn't seem like there was a distribution of particles in this visible size. But the problem is that the collection method was designed inevitably to capture these larger particles. And so when someone went and did another collection method, this time using pumping seawater through a 10-micron filter, you see a much different distribution profile, and you see lots and lots of particles in this smaller subvisible size. So it's not all, and the problem as you think about like how many things that you can probably like look at right now from your field of view and see that's made of plastic or has plastic, and there's probably not very much of it that's exactly the same, right? So you have different types of plastics, you have different polymers that make plastics, you have pigmentation that gets embedded into the plastic itself, and you have composites where you have plastic plus other components, and so those all have different degradation profiles and look different in both visually as well as chemically. So it's not all doom and gloom. So there's this is one example of a paper from 2016 where bacteria have been engineered to degrade plastics. And so we kind of scienced our way into this problem by creating plastic super efficiently and inexpensively, and we'll have to science our way out of it. But to get to a point where maybe we have a better degradable plastic or identified better degradable plastic that also helps us mitigate environments that might be contaminated with plastic. And so it's a complex problem, but it's not unsolvable. But what we ultimately need is some way to identify and characterize the particles that are in the environment now. So this is kind of where I pivot to talk about Hound. And so Hound is a platform that we improved at Unchained Labs and developed to make it where you could basically identify any particle. So Hound in its essence is a microscope with detection lasers incorporated in. So you can do count, size, and morphology of particles that you see on a surface. You can also do identification of those particles with a combination of Raman lasers or LIBS, laser-induced breakdown spectroscopy. From a counting perspective, it works very similar to other particle size analyzers. You put your sample in. The difference here is it's not a flow-based system. It is a surface-based system. So you'd have a filter or a microscope slide-based substrate. You run it through the instrument, and then the instrument automatically counts how many particles are there and automatically does the morphology characteristics. And depending on what you're looking at or looking for, you can characterize and bin into different particle size distributions and can essentially count the number of particles in each bucketed area. The parameters that kind of come out automatically are just width, length, rectangularity, equivalent circular diameter, fibrosity. So these are things that in a situation where you're trying to characterize types of plastics or by appearance, you kind of get all of that information automatically by just the instrument scanning the sample. In terms of sample input, there's two main ways. There's a third way. Let me talk about the easy way first, which is you just put the contaminated material under the microscope. And so like if you had particles on a surface and you wanted to identify those, you don't have to do necessarily any sample prep. The more common ways that people do this, depending on their sample type, is to either filter it. And so we have these gold-coated filter rounds. And so you can add your sample in through that. And there's an apparatus to basically filter through and collect any waste and leave any particles on the surface. And those particles are based, you have a mesh that's different sizes between 0.8 and 10 microns, depending on what you're trying to capture. You also have a capability to look at particles in situ. So for example, if you're concerned that the particle is too small or unstable and it's going to go through the filter, you can put this on this gold-coated surface that's basically a microscope slide, cover it, and then analyze the particle or count particles and analyze them in situ. So the intent here is that there's minimum sample prep needed. So you're not disrupting or losing your particles in the process of trying to capture them and put them on the surface. And then the gold-coated surface improves the analysis method. And so gold-coated is Raman inactive, so we don't have to worry about the signal interfering with a complex spectra or set of spectrum we may see. And also it allows better edge detection. And so especially in something like microplastics, your particles are not necessarily well-defined, and if they may be translucent. And in those cases, a more complex substrate like nitrocellulose would miss those particles. And so by using a better substrate and by using bright field and dark field imaging capabilities, we have more capabilities or better ability to see lots of different types of particles and not miss anything that we're trying to identify. For those of you who are not familiar with Raman, it's a vibrational spectroscopy method. Every material has a unique Raman signature, so even things that appear to be the same. Many of the applications we have for Hound are based on biologics contamination, where people have defined sets of contaminants that may show up in their sample. And so with that, we have two different laser types for Raman that we use. So we have 785 nanometer wavelength Raman, which is pretty much a workhorse common Raman laser and wavelengths, and that takes up a lot of different materials. We also use a 532 laser because one of the, what that does is it works better for fluorescent materials and materials with some degree of color. And so autofluorescent materials like proteins that might show up in a biologic sample work with 532, sometimes mostly better. And then you have cases, a lot of times colored materials will show up better on the 532 laser and have a more distinct spectrum. So between the two of these and the combination of the two of these lasers, we can pretty much identify anything that's going to come in and get a spectrum for anything that's going to come in contact with the sample. So you have a lot of flexibility to identify everything. The particle detection limit is somewhere around 2 microns. And so that also gives a lot of flexibility in identifying particles that are subvisible. There is a manual mode to use the instrument where you can take your sample and put it underneath or just drive around on the stage to determine where your particles are and then fire the laser when you're look at something that you're interested in. The automatic imaging will also allow you to stitch things together. And so if you have particles that are showing up across multiple fields of view, but you also have an automated mode where you can tell the instrument to scan through a certain area of view and then identify a subset, all particles showing up in that area or a subset of particles. And that could be any sort of combination that you decide. So it could be something like to identify every particle that's above 10 microns in an area, or it could be something like you have thousands of particles and you want to say randomly pick 100 particles out of the sample to identify. And so it has perfect tracking of where the particles are located, goes back and does the identification. And then you can also go back and look at, captures, of course, all the images and saves all of them in combination with the Raman spectra. And so when we have systems that have multiple lasers, you can use multiple lasers to go back and do that. So for example, you can do a scan with the 785 nanometer laser, come back and use the 532 laser to identify either everything or particles that you missed or that didn't get a match on the first laser. Today, what I'm going to be talking about mostly is a paper that was a comparison of Raman and FTIR. And so Raman and FTIR are the most common methods that people are currently using to identify contaminants in seawater. And they both have pluses and minuses. And so this paper wanted to do a more systematic, these authors wanted to do a more systematic look at what particles, what is going to be a good technique for going forward. And so the challenges they have are that there's a wide range of particle sizes and particle types that are captured, and then what's going to be the most reliable in identifying microplastics. So their sample collection method, this was seawater collected from the North Sea. So they collected samples through a 100 micron mesh. They sieved these particles to fractionate, and they broke it up into two fractions. One was a particle size over 500 microns. And then they individually picked those out and put them on a surface that could be analyzed by both methods. For the smaller particle sizes, so under 500 microns, they enzymatically cleaned them because, as you would expect, in seawater, you have a lot of organic material or salts that are not of interest here or concern. So they clean the sample to isolate and fractionate out what would be plastic particles. And they used an 8.8 micron mesh filter around to do that capture. So in terms of differences between the technologies, they use ATR, so attenuated total reflectance, FTIR, which generally has a limit of particle size of about 20 microns. Both have pluses and minuses. So Raman, they used the Hound, what is a Hound now, it was called a different instrument at that time if you go look up that paper, but that Hound is generally about under 2 microns, and they use the 785 nanometer laser for that. So while IR has an interference with water, Raman does not. Raman does, at certain wavelengths, have an influence with fluorescence and is challenged by that, where IR does not. And so they broke the study up into 4 different main areas. One is to see if they could manually identify 200 particles greater than 500 microns. Second is to look at a procedure to automatically identify particles in the 10 to 500 micron range. Third is to look at a size dependency of particles between 10 microns to 5 millimeters to see if either technique was influenced by that. And then finally, they attempted to do an analysis of particles in the 1 to 10 micron range, but they focused that specifically on the Raman instrument. First, on the particles above 500 microns, they started with about 200 particles. The Raman could identify 140 of those particles, and the FTIR could identify about 114. So there's about a 23% difference in terms of how many particles the Raman could identify versus the FTIR. The FTIR was challenged by some of the particles being too small. So while the particles were separated by a high dimension of 500 microns, that doesn't necessarily mean they're 500 microns across like a sphere, or it's more like there's a high dimension of 500. So if you had a 500 micron particle and a thinness of 10 microns, like a fiber or something like that, the FTIR struggled with that. The FTIR also struggled in some cases with the presence of dye. From a Raman standpoint, there was the limitations were particles that were very dark or strongly absorbing, and fluorescent particles. You can see from looking at this graph that both of them do a fairly good job of identifying particles that are polyethylene or polypropylene, which are the black and the aqua green, aqua blue colors. And then at the top of the Raman, you see a lot of advantages in identifying particles that were polyester and fibers that were missed by the IR technique. For smaller particles in the 10 to 500 micron range, there was a much starker difference between the two. And so the FTIR captured about half of the particles and identified half of the particles that the Raman instrument identified. So it's important to note that these were the same particles. They were analyzed by both methods. So the gold filter round was used on the Raman instrument and then taken to the IR instrument. So there was not a disruption or movement of particles that influenced their ability to be detected. The Raman identified more polymer types. So it identified 19 polymer types where the IR instrument was only able to identify 10. And you can see again, there's this pretty big discrepancy, especially at the top of the curve, at the top of the bar, of types of polymers that the Raman is identifying and the IR is not able to do so. In terms of looking and comparing the size distribution relative to the types of particles, they're basically across the board, Raman identified more particles independent of the size of the particle. And so that was much more a function of the capability of the instrument versus a specific size. So out of about 450 particles, there's about 135 that both instruments identified. There was 268, so about half those particles were only identified by Raman, and about 15% or 76 particles were only identified by FTIR. And you can see a pretty stark difference, especially at the larger part of the larger population set of the 10 to 25 microns, where the Raman is able to detect about 50 or 60% more than the IR. And in the 25 to 50 micron range, there's about a 5-fold difference in the Raman instrument being able to identify over the FTIR instrument. Finally, they attempted to look at particles in the 1 to 10 micron range. Many of those were identified by Raman. And in this, even cases where the practical limit of the instrument is 2 microns, of the laser is 2 microns, it could still pick up and identify particles in the 1 micron range. So the key findings and key takeaways is the Hound identified more particles. So the Hound identified about 23% more particles than the FTIR instrument. The Hound identified twice as many particles as IR in the 10 to 500 micron range, and including not just by particle size, but mostly on certain material types that the IR instrument missed. And the Hound was able to identify particles under 10 microns. In terms of looking at the overall assessment, the characterization from the paper, the pros of the FTIR instrument is much more robust in identifying pigmented microparticles and reliable for particles greater than 500 microns. The advantages of Raman is that it had a higher ID rate. So about 91% of the particles studied in this paper were identified by Hound. It had more flexibility in terms of the types of particles it could identify, and it had a broad range of reliable identification across the range of particle sizes from 1 micron to 5 millimeters. The other advantage of Hound, or of Raman in this case, is that it could be used fully automated. And so you could set up the instrument and walk away, whereas the IR instrument, you needed a lot more hands-on time to do that. On the con side, from the FTIR, you had a lower ID rate, missed more particle types. There was a sensitivity to fibers and thickness of the particle, which could interfere with identification. Challenge on black fiber particles, and was much more manual. For the Raman instrument, pigment had interferences, so fluorescence and absorbance issues, also struggled with black fibers. I do want to point out, like on this paper, they used solely a Hound 785 instrument. In our cases, what we would do is, in these cases where we weren't able to identify by fluorescence, there's capabilities of the instrument to do an auto burn or to remove some of the autofluorescence, or to switch lasers to the 532 nanometer, which was not available to the researchers here. Now, in terms of the database, so there's a lot of different types of plastics and materials that can come in. We sell the instrument with a kind of a core set of materials that could show up. So that's 150 Raman spectra and about 50 laser-induced breakdown spectroscopy references. So those are generally developed as fit for purpose, right? So we don't have a 20,000 spectra reference for someone to search through. People who buy and get the instrument will oftentimes develop a set of reference materials that's specific to their processes, or develop one over time. We also work with, we have a contract test lab in-house, and so we also work with customers to help them identify those reference spectra. Creating your own reference spectra is fairly straightforward. You take the material, you scan it a few times, it averages the spectra, and then boom, it's in your reference library. And then that gives you much more specific references that you can capture and identify by. If you're using it over multiple sites, you also can import and export spectra from multiple sites if you create a custom reference library that's specific to the materials that you're interested in. So overall, I hope in a brief discussion today, I've given you interest to go look at the paper, which we're happy to share the reference with people and show kind of just some of the capabilities about Hound. So Hound can identify microplastics in a very small size at a very high identification rate. It can do this in a manual mode or an automated mode. You have the flexibility to filter. You have the flexibility to look at samples in situ, and you can have an expandable spectral library that you can develop, and we can help you develop specifically for your material types. So any questions, please feel free to go to the website, unchainedlabs.com. The product again is called Hound, or contact us at info@unchainedlabs.com. As we mentioned, we'll do questions now, and thank you so much for your attention and time.
Thank you, Joe, for talking us through all of that. That's a very interesting, if not slightly disturbing, analysis of just how much plastic is in our world. But luckily, it sounds like Hound is able to identify that plastic, and hopefully that identification can lead to some prevention.
Yeah, it's crazy, you know, like we're both scientists, and so I didn't really study this area a whole lot before I started, and then I looked at this and looked into it more, and I was like, it really kind of weighs on you when you're after you're making the slides and thinking about this, because it's not something you normally think about. So I needed a couple days, and I needed to go find references to, okay, someone's working on this. That's good.
Yeah, it's good to know.
Yeah.
So with that, we have some great questions that have already come in through our chat. So we're going to go through those. I just want to remind everyone that you can still ask questions at this point. The way that you do this is go to the Q&A button in the Zoom navigation bar, either at the top or bottom of your screen. Type up your question and we'll get through as many of them as we can. So with that, let's look at our first question for you, Joe.
Okay.
What are the laser options for Hound?
Okay, so as I mentioned, this paper did specifically a Hound 785, which is a red laser. So we sell these in kind of configurations. So we have a dual laser, like a 785 and a 532. We do 785 and LIBS, which I didn't talk about today because it wasn't relevant to the paper, but that's much more specific for elemental and metal contaminants. And so we have those two dual laser options. The paper was done in actually, I think the data was collected actually earlier, like 2014 or 2015. The paper came out in 2018. Unchained Labs revamped the instrument in last year, And that gave us the ability to do a triple laser, which is the 785, 532, and LIBS all in one machine. And so since we launched that last year, that's been kind of the dominant one that's been used by people, because you can catch everything.
How long does it take to count these particles?
Yeah, so it's somewhat dependent on the surface area that you're scanning. So, like for example, if you're looking at like an 18 millimeter by 18 millimeter, that's the one that's in my head. It's about 9 minutes to scan and do the counting.
Okay, and then there's a question in here about what is the difference between normal FTIR and the ATR FTIR that you brought up?
Okay. So normal FTIR, if for chemists in the audience, is mostly detect sample through transmittance. And so you may remember like having, depending on what kind of lab classes you took, having to kind of press your sample into a salt pellet and then transmit through that. So obviously impractical for something like this. So ATR is called attenuated total reflectance FTIR. So in that case, the sample is placed on a crystalline surface and then IR reflections bounce off of it. So the advantages of that are that you can work with three-dimensional particles and it works better for smaller particles, and that simplifies sample prep. And so that allows people, the Hound can obviously just, it's on the surface and can read it, but it kind of leveled the, made it more of an apples to apples comparison because we're looking at native particles between the two.
And then how long does it take to identify the particles by Raman?
Yeah, so this is dependent on the complexity of the particle and the number of particles. So I kind of, again, I have a benchmark in my head that I use, which is like 200 particles can be analyzed in about 30 minutes in an idealized case. And that's like, okay, very low laser power and very short exposure time. So in this paper, they used high laser exposure time for the larger particles, so about 30 seconds per particle, which is definitely on the long side, and then shorter times, 10 seconds for the smaller particles. So longer exposure at lower laser power for the big particles, higher exposure or shorter time and higher laser power for the smaller ones. As they said, they used a smaller and older instrument, and supplemental information, maybe in the real paper. They said it's about 43 hours unattended for about 5,000 particles. And I say the old instrument because I know in the new instrument, one of the things we did was we optimized the path of identifying sample particles so that it much more efficiently steps through. But I don't have those numbers to compare, but yeah.
And then was there a reason that the larger particles were not identified with the automated mode in this study?
Oh, they did, but I just didn't talk about it specifically here. So they took 100 particles and analyzed the filter round. And so what they did is they did that automatically, and I don't recall seeing the time on that, but what they did was they also looked at robustness of the detection method since it's a rough 3D surface. And what they did is they imaged this area, about 100 particles. They captured, I think, 95% of the particles, identified 95% of the particles, and then they rotated that filter 90 degrees for 4 times and then tried to do it again. And so the idea is if you're missing the particle or somehow that's not robust enough, you're going to miss the identification or not match. But it did match in every time they did the rotation of the filter.
Awesome. And then going back to look at kind of sample prep related stuff, can you tell us more about the filter handling and the sample prep for the filter rounds? For example, how is it kept flat to assist in maintaining a single plane of focus, and kind of how that whole process works?
Yeah, so the filter round itself is, if you kind of hold it up, it looks it doesn't look flat. And so to capture particles on it, we have it as a vacuum filtration. And so there's a specialized piece of glassware that it sits on, gets clamped in, and so you're filtering it and the vacuum, flattens it out. For reading on the instrument, there is another little ring that goes around the filter round, and then that holds it flat while it's on the stage.
And then once you've collected all this data, can you tell us more about the options for post-spectral capture processing? So can you do spectral smoothing or fluorescence reduction in the post-spectral processing?
Yeah, I might defer to you on this one, Will Robin, but you can certainly do post-spectral processing. And so there is some level of sample analysis or spectral analysis that you can do post-data collection.
Yes. Just for a little bit more clarification, you can do smoothing, you can do detrending, you can do normalization, you can subtract background. There's all kinds of spectral processing that you can do with this instrument, and you can export your spectra any way you'd like.
Thanks, Robin.
And then looking at maybe a more complex particle, can you use Hound and Raman to analyze combination particles? For this example is microplastics on dust particles, or I also thought of dusty microplastics or stuff like that.
Yes, so you do have capabilities to do in a manual mode. Let's say the particle looks complex. You can go to different points of that particle and identify. You also have the capability in an automated mode to go back and identify. There's a couple things. You have the automated mode where you could set it up where I'm going to go through and read the whole thing with a 785 nanometer laser, and then go back and either identify everything again with a 532 or a LIBS, or go back and only identify the particles that are missed, that weren't identified from the first pass. There's a verification mode on the instrument that if you're not, say if it didn't get a match on the automated parameters, you can go back and look at that. And then at that point, you can look at the other lasers as well, especially if you see the particle looks amorphous and you want to pick a different spot in that particle to identify.
Awesome. Well, it looks like we got through quite a few very good questions. Just a reminder to everyone, if you didn't get a chance to submit your question during this, you can feel free to email us at info@unchainedlabs.com. Even if you want to have a deeper conversation or get some more specific information, please just email us at that info@unchainedlabs.com or visit our website at www.unchainedlabs.com. We'd love to connect with you, and we thank you again for attending our virtual seminar. Hope you have a great rest of your day.
Thank you.